There's a number of classical example stories with which the problem of secure computation is usually introduced, and one of them is this millionaire's problem. So Alice and Bob are now egotistical millionaires. Alice's net financial worth is X1, Bob's is X2, and they want to know who is richer. That means they desire to compute this Boolean, which takes value true if X1 is bigger than X2 and false otherwise. That would be easy enough, but the difficulty is that they don't want to reveal their net financial worth to each other. In other words, Alice doesn't want to reveal more about X1 than Bob than necessary, and vice versa. Secure computation is the tool that enables them to solve this problem. It delivers to them a protocol. The protocol tells them how to compute and send messages to each other, to interact, in other words, for a few exchanges. And at the end of that, each of them will have output, which is this desired result. Nonetheless, although they each get that output, neither learns anything more about the other party's input than, of course, is revealed by the fact of this output. Now, this is the description of secure computation, but something that's worth keeping track of as we go along is that there is some loss of privacy inherent in the fact that the result of the computation is revealed. In particular, if y is true, then Alice knows that x1 is bigger than x2, meaning she's richer, and that gives us some indication of Bob's net worth. It's something in this range. Conversely, if she learns that she makes less, then she knows that Bob's worth is in this range. So when we say Alice learns nothing more about x2 than given by y, we mean that she learns nothing more than what's indicated here. So we're going to start studying this problem by trying to formalize a little bit better the task that we're trying to solve in the sense of what we're trying to compute. And that object will be a two-party functionality that will be specified by a pair of algorithms which operate like this. The first algorithm is kind of an initial setup. What it does is it generates quantities that we'll think of as keys, which are long-lived. There'll be one for the first party and one for the second party. Once these keys are in place, the parties provide inputs, x1 and x2 respectively, and then the functionality tells us what outputs they want to get. So it says party 1 expects to obtain this, party 2 expects to obtain that. Notice that this is not the protocol. It's telling us what we are shooting to achieve. Think of these inputs as changing in the sense that once the keys are in place, we may have many executions which with different choices of these inputs. It's useful to denote the output of the ith party in this way. And also, while keys are sometimes useful, they certainly aren't always. And when they're absent, we'll refer to the functionality as keyless, and then we may just omit it as a subscript. As an example, we can write a functionality to capture the millionaire's problem like this. The functionality is keyless, so there's no subscript. It takes Alice and Bob's input x1, x2, and it simply computes the result, the Boolean whether x1 is more than x2, and returns that. Okay. So again, this is our goal description. So then what is secure computation? It's a protocol whose job it is to securely compute a given functionality. So with this functionality now fixed, what we imagine is that party 1 is initialized with its initial input or key as given by the functionality, and also by its current actual input x sub I. Now the parties interact. That means they compute and send each other messages back and forth for some number of rounds. And at the end of that, each of them has an output. The formal description of a protocol, which would, in our usual language be what we call the syntax, would have the job of saying how these parties compute and send messages to each other. It would be an algorithm that, given a incoming message and given either the party's coins or current state, computes the outgoing message. And at the end, from all the messages received, computes the output of the party. But we won't usually specify that in detail. We'll just have these little pictures. There's of course a correctness requirement, and that simply says that correctness of the protocol relative to the functionality we're looking at says that the outputs are what the functionality says they should be for each party. And finally, there's privacy. And what privacy says that any party learns nothing more about the input of the other party than what is revealed by the output that it has received. Now, of course, we haven't here given a formal definition, and we won't, but these definitions are not necessarily simple. They're quite subtle, and the literature has many attempts and a lot of work which tries to give good definitions for secure computation. It also has a bunch of different settings which vary in the kind of power that the adversary has and so forth. And of the main ones here is what's called the semi-honest setting, or also sometimes called the honest but curious setting. And here the assumption is that each party desires to learn as much as it can about the other party's input, but when it runs the protocol, it follows the protocol instructions. If the protocol says compute and send a message in the following way, it will do that. However, when it gets a message from the other party and in the end looks at everything the other party sent, it gets curious and it'll try its best to compute from what it knows the other party's input or learn something about it. However, we may also consider a more adversarial setting, usually called malicious. Here, the party that wants to learn the other party's input will deviate from the prescribed protocol. If the protocol says compute the message you're supposed to send in the following way, it'll say, maybe not. I'll instead compute it this other way because I think doing that will allow me to get a response which is more helpful towards figuring out the other party's input. In our discussion here, we're only going to consider the semi-honest setting. Now, when cryptographers approach a new problem, it's typical to ask whether we can give a general solution. And what that would be here is to say, suppose I hand you any two-party functionality as described by this pair of algorithms, and I ask you to design a secure computation protocol for it. Can you do that? And curiously, the answer is yes. Now, this was known for some time, but currently probably the simplest way to see this is to use fully homomorphic encryption. So let's fix a scheme that's fully homomorphic, and we'll assume it's an asymmetric encryption scheme. Remember, this means that you can homomorphically compute any function. It turns out that the specific function we're interested in here is this one. It's the functionality output. We'll let f on input the long and short-term inputs of the parties, compute the functionality, and return the output that should go to party 1. In this illustration, we're assuming for simplicity that party 2 has no output. It's quite easy to change this around so that you can also deliver party 2 its desired output. So now here's our protocol, which we'll call PyFHE. So party 1, given its key and its input, begins by generating keys for our FHE scheme, encryption and decryption key. And of course, in the asymmetric setting, the homomorphic evaluation key is just the encryption key. And it sends all these keys over to the other party. These are all public, effectively. It now encrypts its inputs. Both the key and the current actual input are encrypted under the encryption scheme, and the ciphertexts are sent to the other party. At this point, party P2 doesn't really learn anything about the inputs of party 1 because all it gets are ciphertexts. So what does it do? It has the encryption keys So it also encrypts its inputs. So now it proceeds to create encryptions of its key and its actual input x2, call them C2 and D2. Okay, now what? Does it send those back to the party 1? No, that would be foolish because this party actually has the decryption key. If party 2 were to transmit these ciphertexts back, party 1 could decrypt them and completely learn all of P2's inputs. What it instead does is it runs homomorphic evaluation on these ciphertexts and these ciphertexts with this function. So clearly, the result of that is that this ciphertext encrypts F of these inputs. In other words, it encrypts the result that party 1 wants to get. So now it sends this back, this ciphertext, and our party 1, who has the decryption key, can decrypt that and recover exactly what we want. And so there we go. That's a pretty plausible looking protocol. And this works once you properly define the goals and analyze and prove everything. There are other protocols, in particular ones that precede this. The sort of canonical way to do a secure computation for an arbitrary two-party functionality is to use two tools. One is circuit garbling schemes, and the other is oblivious transfer. Oblivious transfer is itself a kind of simple two-party protocol. And over time, there's been a greater and greater amount of practical interest in two-party computation, and this has led to optimizations and efforts to make the primitive faster. And in particular, garbling schemes by now are quite fast, and so is oblivious transfer. And these protocols do execute relatively quickly. But for various reasons, they're still not entirely practical at least for complex functionalities. With current fully homomorphic encryption schemes, although the protocol we gave before is conceptually nice and simple and understandable, it's probably even less practical. So one consequence of all this is when people come to seeking practical secure computation protocols for functionalities that they actually want to compute, they will often seek what we would call dedicated protocols, meaning ones tailored to the specific functionality they want, and there they can find interesting, efficient ones. So we'll discuss a couple of related examples. One is oblivious pseudorandom functions, and the other is what's called private set membership, a special case of what's often called private set intersection. So we'll begin by stepping back a little bit, because in Oblivious PRFs, we'll need PRFs with a little more functionality than we've seen earlier. So let's go back to a function family. That just means something, a deterministic algorithm that takes a key, some input, and gives you an output. And we'll talk of something called a public key deriver for it. That's a function that takes the key and gives you back some output. And intuitively, we want to say that the output of this function on the key is going to be provided or revealed to the adversary. And we want that the PRF security of F be maintained even given that true. So the requirement would be that we pick a key K, we compute X, which is the public key deriver on it, give it to the adversary, and then look at the PRF games and ask that the adversary still not be able to win. So we need for that to extend the games. The games are still real and random. They're now parameterized here by the function family and this public key deriver. And in this case, while they used to be parameterized simply by the range set R, we'll put the whole function family and the public key deriver. The initialized procedure for both now picks a key at random, computes this public quantity on it, and this is the new element that has a return statement giving this to the adversary. It has to be done exactly the same way here, even though in this game the key is never used, but it's used for the purpose of deriving this X. These oracles are the same as in the usual PRF case. You provide an input to Fn, you get the result of f under the hidden key in the real game. And in the random game, you just get a random non-repeating quantity as chosen over here. And the advantage is defined as usual. We still call it PRF. The subscript now includes our public key deriver, and it's the difference in the probabilities that the adversary outputs 1 in these two games. And notice that the PRFs that we know and love from before are the special case in which the public key deriver just returns the empty string. So we've generalized the prior notion. Now, why do we want to do this? Because there are some examples of PRFs which we will be using as the basis for Oblivious PRFs, and those protocols will use these public functions of the key. And so here we're going to give an example of a PRF with a public key deriver, which we will later see admits oblivious evaluation. So far, we've tended to think of PRFs as primitives that we get using tools like block ciphers and hash functions, but you can equally well get PRFs from number theory, and that turns out to be useful here because it's the algebra and the number theory that allows us to do the oblivious evaluation. So here's our PRF. We fix a cyclic group G. We let M be its order and little g be a generator. We'll have one hash function whose range is the group, and another whose range is the set of strings of some length L. Our PRF has a key space which is Z mod n, M, which means the key k is an exponent. It takes an input of arbitrary length and it has an L-bit output. And now we define both the function and the public key deriver. So we write the function as having oracle access to the hash functions because in security analysis they're going to be random oracles. It takes the key and the input. It hashes the message input. That gives it a point in the group. It can now raise that to the power the key, which is an exponent, and we'll call that y. Now, in some intuitive sense, this y is the result of the PRF, but we're not quite going to output that. What we'll actually do is further hash it with the message to get an L-bit string, and that's the actual PRF output. What is the public key deriver? The thing we are going to be interested in revealing is g raised to the power of the secret key. And that's what we consider known. So now we're going to claim that this PRF, this function f is PRF secure given this key deriver, which means it meets the last definition, and which means PRF security of this is preserved even if an adversary knows this function of the key. And it turns out you can prove this in the random oracle model for the hash functions, assuming the computational Diffie-Hellman problem is hard in G. We won't do that proof. Given the techniques we have, it's not terribly bad. All right, so now we turn to oblivious PRFs, and we'll begin by specifying a functionality because the functionality tells us what exactly we're trying to compute. So we'll fix a function family. This is going to be our PRF relative to this public key deriver called P. We're giving here a general definition, but you can keep in mind the previous example as the one we're going to be eventually interested in. So here's the two-party functionality for oblivious PRF. What it does intuitively is that it's going to ask party 2 to maintain a key k for the PRF. So initialize will be responsible for picking that key, and as you see here, party 2 now holds it. Party 1 will be given the public key deriver applied to the key, so that extra information. What are we actually wanting to compute? Well, party 1 enters with a certain message. Party 2 has no input. And what party 1 is asking is it's saying, I want to know simply the result of the PRF under your party 2's key applied to my message. And so that's its desired output. And party 1 doesn't want an output at all. Okay, so what does this mean in terms of secure computation? It means that party 1 will obtain the result of the PRF under K on its input without revealing that message to party 2. So that's the privacy guarantee here. Party 2 does not learn the message, nonetheless party 1 learns the output. There's also a security guarantee on the other side. You don't want party 1 to learn the key. It shouldn't be able to, in particular, evaluate this function fk on any other message than the one through which it interacted with this other party with here to obtain this result. Okay, so that's what we want. That's why it's called oblivious. So let's try to build this thing. So, and we're going to do this for the particular example PRF that we had before. So we fix our cyclic group with generator G, the group has order M, we fix our 2 hash functions, and F as before is the functionality. Remember what it does is that it hashes the message to get a group element, raises that to the power the key, and then hashes again. So now party P1 has the message and it has this public key corresponding to it, which here is G to the power K. Party 2 has the actual key K underlying the PRF. And what party 1 wants is to obtain this quantity here, which is the function applied to M. Okay, so what does it need to do that? Well, it needs to compute the hash of M raised to the kth power. Once it has that, it's very easy to get the Z value because that's just a public hash of the value Y, which is this to the kth power. So how about the following? It hashes the message and it sends it over. And it asks party 2, please raise that to the power K, which you can do since you know K, give me back the reply. And then I'll hash that with the message and output Z. Okay, well that works in the sense that it is correct. This is the correct value of the PRF we're seeking. But unfortunately, this is not secure. It's not providing privacy. Why is that? Well, maybe party 1 thought that by hashing M, it's hiding M. But this is not true. No matter how good the hash function, some deterministic function of it computed like this doesn't hide it. In particular, if as well may be likely, the message comes from a small space, it's very easy for the second party to completely determine the message by just searching through that space and hashing the candidates. So this isn't quite going to work. So now party 1 is a little more clever with exactly the same setup as before. It says, okay, I want to obtain hash 1 of M to the power K, but I can't send you hash 1 of M directly. So instead what I'll do is I'll blind it. Blind it means I'll multiply by a random group element before sending over. That random group element has the form G to some power, where this party also makes sure to know what that power is. It selects it itself at random. Now when party 2 gets this and looks at this, it can determine nothing at all about even the hash of M, let alone about M. Why is that? Because this is just a random group element. Its job, however, is the same as before, to raise this thing to the kth power, where K is its key. It does that and ships back the result. From this, we now want party 1 to recover hash 1 of M to the K, and we claim that this formula does that for it. It takes the Z. Remember that X here is G to the K, and this is where we use that this party knows this X, and it raises that to the power negative B, or if you like, it takes the inverse in the group and raises that to the bth power. Let's begin by just checking that this works. So what happens when you take Z times big X to the negative B? Well, Z is B to the K, because that's what it's computed as here. So we have this. Now we fill in that B is this, hash 1 of M times G to the B, and we also know that big X is G to the K. And so we get that. And now looking at these, clearly these two things go away and you get hash 1 of M to the K. After that, it's simple to get the PRF output. You just apply the second hash to this value y in the message, and by definition you get this. Okay, so we now have a candidate protocol which is correct and looking much nicer, at least, than our naive attempt. So let's see what we can say about privacy. Now this is of course always a little delicate because here we're reasoning in the absence of precise definitions, but intuitively it's very clear, hopefully, that at least in our semi-honest setting, party 2 learns absolutely nothing about the message. Why is that? Because what it sees is simply a random group element, and that gives it no information at all about M. What party 1 learns is a little more delicate, but what we can argue is that it doesn't learn anything beyond the value of the PRF on its one input M, and if it interacts twice with this party, it doesn't learn anything beyond the value of that PRF on the two inputs in those two interactions. And this corresponds to the function being a PRF. So we'll leave it as that, which is hopefully enough. All right, so what makes Oblivious PRFs interesting? They actually have a slew of different applications and usages, so they're evolving into a quite common, versatile, and powerful tool. One of these is an application called Callisto, which is a serial sexual assault prevention and protection tool. So what happens on Callisto is that a victim can identify or report a perpetrator while preserving their privacy, or the victim's privacy. And Callisto then encrypts this perpetrator identity. And then what it does is it ensures that if two victims report the same perpetrator, then it's detected, and then the information is passed on to a lawyer or something like that. And otherwise, all identities are protected. And as part of this, we won't say how, but it's not terribly complicated. It's kind of a nice protocol, and Oblivious PRF is used. So you can look at their website and learn more there. It gives you the whole context about sexual assault, and it has portals for reporting. So it tells you about the matching system, allows you to create a record, and so forth. So kind of a nice application of secure computation. All right, now we'll move on to another functionality, which in the end is itself an application, at least in one way of realizing it, of Oblivious PRFs. And this is what we'll call private set membership. So again, we're going to start by describing the functionality, which is the object we want to compute, and thereby effectively saying what is the problem. So it's a two-party keyless functionality. The first party's input is a message. The second party's input is a set. And what we want to determine is, does this message or input belong to this set or not? So D here is the Boolean, true if the message is in the set and false otherwise. And party 1 gets that back as a result. Now, it turns out that protocols for this tend to reveal also the size of the set S. And to make our life simple, we'll simply put that in the output for party 1. Not because we love revealing the size, but because we seem to find it relatively inevitable. Party 2 here gets no output. So again, then what does a secure computation protocol for private set membership do? It means that party 1 is going to, after the interaction, learn whether its input is in the set held by party 2. But party 2 does not learn what input party 1 was testing for. It doesn't learn the input of party 1. And also party 2 doesn't learn anything about the set beyond whether this particular input is in it or not. Now, private set membership is a special case of something called private set intersection. This is a more general problem in which the input of the first party is also a set, and what we're looking to get for the party is the intersection of the two sets. In other words, it must learn all the points that belong to both sets. And you can see that private set membership is the special case in which this set has size 1. So that intersection is either M itself, in which case M is a member of S, or nothing, in which case M is not a member of S. So this has a number of interesting uses. One of them is represented by services like Have I Been Pawned. So the setup here is that various services on the internet collect and form kind of lists of breached credentials. So these are, a credential is either a username or a password or a phone number or whatever, and some breach has compromised this. So they collect these up, and now if you as an individual have a credential, it may be useful to you to know whether or not that has been in a breach. And because if it has, you probably don't want to be using it anymore. So these services allow you to check that. You can effectively see whether your credential is part of the list that they maintain. The difficulty is that, of course, you don't want to send your credential to the server because, of course, your credential has a lot of privacy attached to it. It's your password. And so we want to make sure that's not revealed to the server. And that's where private set membership comes in. Now, on the other hand, you actually also don't want the server to simply make the list of breached credentials public, because that'll just increase the extent to which they can be exploited beyond even what they were exploited through whatever breach they were involved in. And so PSM, private set membership, will solve this problem for us. And you can see how that looks over here. This is the actual web page. You can enter your things here, and then it tells you about the different breaches. It tells you about different breaches that have recently occurred where it's added the information to its database. And as you can see, there's a lot of websites which have been pawned and a lot of accounts as well. And there's been a lot of checks that have been done using this. So again, quite a nice application of private set membership. Here's another one, which is called private contact discovery. So consider something like the Signal private messaging app. If you haven't run Signal, maybe run some other secure messaging app. But all of these have a set of users, and they encrypt information end to end, so that even the server doesn't know what's being communicated. But Signal, at least, is also concerned with whether your contact list remains private. So if you want to contact someone, you may need to first contact the Signal server to see if they have an account on Signal. And Signal would like to enable you to do that in such a way that you don't reveal your contact to them. And one way to do that would be via private set membership. So here the set would be the single contacts, and then you would be checking whether your contact is in there. Now, there's a lot of background and sort of motivation here. Signal tells you it's social software, and that they have a culture of privacy, and they want in particular to make sure that the contact discovery is private. Now, it turns out that they don't actually end up using private set membership for various performance and other reasons. But in principle, it was a way to solve the problem, and probably the first thing that comes to mind. Okay, so having sufficiently motivated, hopefully, private set membership, let's see how we might accomplish that. And to this end, we're going to exploit an Oblivious PRF protocol. So we let F be a PRF, and we let P be its public key deriver, and we let this denote the protocol, which means messages going back and forth between the parties to compute the functionality of the OPRF. You can think it's the example protocol we had before, although that's not needed here. This works regardless of what protocol we use. We come now to PSM. So party 1 has its input message, party 2 has its set. And we want to know whether M belongs to S. So what party 2, the server, does is it picks a key for the PRF, and it computes the public key information corresponding to that. And it begins by sending that public key information over to party 1. Now, why does it do this? Only because this protocol may use it. It doesn't need it beyond that. More importantly, what it does is it applies the PRFF under its key K to all the points in its set, and thereby creates effectively what you can think of as a kind of blinded or encrypted version of the set. And that whole blinded set is actually revealed to the first party, or in practice maybe even made public so that you don't have to repeatedly send this to different places. Now, what party 1 wants to do is compute f sub k on its own message M. Why does it want to do that? Because it can then just test if that value belongs to this set, and that's effectively testing whether M belongs to the original set. But if it wants to compute f sub k of M with k held by the server, it certainly doesn't want to reveal M, so it's not going to send M over. So what enables it to do this is our Oblivious PRF protocol. It will now input to that protocol its message. The protocol will use this public key identifier, public key derived value. On the other side, the party number 2 will input the key, and the result will be f sub k of M. So all that this party now has to do is check whether that belongs to this set of encrypted members of this set. And it outputs that Boolean, and this as its estimate of the size of the set S. Okay, so that's our protocol. And we can now start thinking a little bit about its different properties. We'll start with correctness. So remember what that means is we need to know that this is the Boolean corresponding to whether M is in S, and that this is the size of the set S. And there's a little bit of a wrinkle here, namely that depending on how many collisions f sub k has, this set T could actually be a little smaller than the original S. Furthermore, it could be that Z belongs to T and yet M doesn't belong to S because f sub k had a collision. But we can get around those things, but let's kind of think of it as f sub k not having collisions. And in that case, we see that we do have correctness, because in that case, M belongs to S exactly when Z belongs to T, and the size of T is exactly the size of S. We can then consider privacy. So we need to ask separately, privacy for P1 means it wants to ensure that its own message M is not learned by the other party. But this we can guarantee through the OPRF protocol security. And in particular, if we use the protocol we saw before, then party 2 learns absolutely nothing about the message M. What about privacy for P2? P2's concern is to not reveal anything more about this set than the fact of whether or not this message M belongs to it. And that can be argued based on the fact that this function f is a PRF. So effectively, that's arguing that these values aren't really revealing anything about the set S other than its size. And similarly, this is not revealing more than what it's supposed to. But again, this is delicate because we haven't actually given a definition. There are many possible ones, and this is far from being a full rigorous claim, and certainly no proof here.